Hello everyone. Today we'll be looking at the four key geological theories. These include continental drift, convection currents, seafloor spreading, and plate tectonics. So without any further ado, let's just jump straight into them. Firstly, let's look at continental drift as it was the first to ever be discovered. Now, continental drift was a theory proposed by a man called Alfred Wegener. Now, Alfred Wegener believed that all the continents on the Earth had been once joined together into a single landmass and they had since drifted apart. So he believed that all the seven continents, they were once connected into this large supercontinent which he called Pangaea. And since then they had slowly over geological time, which is a really long time, they'd moved apart. So if I was to give you a proper definition, it would be something along the lines of this. Now, obviously, he proposed this theory, but he would have needed evidence to support it. So then, the key pieces of evidence that he gave four key pieces of evidence to what he found. So let's look at each of these pieces of evidence. The first evidence was the apparent affinity of continents. When Alfred Wegener first looked at the available map of all the seven continents and all the countries, he found that the east coast of South America fit in nicely with the west coast of Africa. Similarly, he found that Africa, Madagascar, and India all seemed to come together and fit as well. So he saw this jigsaw fit, which made him believe that this could only be possible if these continents had been once connected. So when we're talking about the apparent affinity of continents, we're talking about how they fit nicely in just like a jigsaw puzzle. So essentially a jigsaw fit. Now, the second piece of evidence that Alfred Wegener found was fossils and their distribution. What Alfred Wegener found that most of the fossils of many ancient extinct animals were found such that when you connected these continents, they would connect these fossils and their parts would connect as well. For example, Mesoceras, a freshwater reptile, was found in the southern areas of South America and in the southern areas of Africa, and it was found such that when you connect them, so would the fossils, so would the existence and findings of these fossils, which led to this belief that it must have been that these continents had been connected at once. Because let's be honest, most of these were reptiles, and for example, the freshwater Mesoceras, it could not live in salt water, right? So it couldn't have traveled from South America to Africa or vice versa. So it honestly suggested that these continents must have been connected before. So a key example to remember when talking about fossils and their distribution is the Mesoceras. Because the Mesoceras was a freshwater reptile, and so it's not really possible, as you can see here, for it to travel from South America to Africa. Now, another piece of evidence that he gave was landforms and their distribution. Alfred Wegener found that mountain ranges in South America and mountain ranges in Africa lined up. Similarly, he found that European coalfields, they also matched up with similar coalfields in North America. Now, the distribution of rocks and their similarities could only be possible if they had been connected at one point and had been formed back then, and then they had drifted apart, which would also cause these landforms to separate. Now, fourthly, and this is a bit confusing, the last piece of evidence that he gave was tillet deposits. So basically, tillets are sediments deposited by glacier ice. So when glaciers moved through these continents, so basically glaciers are rivers or sheets of ice that flow across the land surface, and they often carry grains and sediments, and these grains and sediments are often deposited and these deposits are known as tillets. Now, one thing that we know that Alfred Wegener found that these tillet deposits were very close when you connected the continents. Now, glaciers could not travel between seas, so it must have suggested that these glaciers had traveled in areas where these continents must have been connected. So that's also a proof that he had. And these were the 4 proofs that Alfred Wegener had for continental drift. Now, the key thing to understand is that although Alfred Wegener had proof, he did not have a satisfactory mechanism that explained why these continents actually moved. He suggested that it could have been because of the sun or moon's gravity that would have pushed the continents out of their place, but there's just not enough energy in their gravity that would move them. And so, because he didn't have an apparent mechanism that explained, the theory was rejected. So continental drift was rejected. After that, we got convection current theory. So let's quickly take a look at convection current theory. Now, really quickly before we jump into convection current theory, I thought I might explain the last piece of evidence in a bit more detail. So tillet deposits, although it sounds pretty simple, it is quite hard to understand. So tillets are basically sediments deposited by glacier ice. Now, glaciers are rivers or sheets of ice which contain sediments. And when these ice melts, these sediments stay in a fossil, which is called a till. So technically, it's like the fossil evidence with the Mesosaurus that I talked about before, but in this case, it happens with the movement of glacier ice. Now, these tillets or sediments deposited from glacier ice were found in multiple continents over a singular path. Now, if these continents were disconnected, it would be difficult for the glacier ice to span all the way through. But if these continents were connected, all the tillets or all the tills would follow a simple path, and it would make much more sense. And hence, this also suggests that the continents were in a way connected at one point. And now, because Alfred Wegener didn't have any apparent evidence or mechanism if he didn't have any apparent mechanism to suggest this, that is exactly why his theory got rejected. Now, with convection current theory and seafloor spreading theory, these actually bring evidence into and bring suggestions and bring mechanisms that explain why there's been movements in Earth's crust. So let's quickly take a look at convection currents next. Alright, so now that we've looked at continental drift and especially understood how tillet deposits work, let's now look at the convection current theory. Now, this was a theory proposed by a man called Arthurholmes. Now, the convection current theory is quite simple. Just like how we have learned about convection currents in when you heat up a beaker or something like that in chemistry, what Arthur Holmes suggested is that, similar to that, there's convection currents in the asthenosphere, and the asthenosphere is, so firstly let's understand the asthenosphere and the lithosphere. So the lithosphere is the solid portion of the Earth's surface, so Earth's layers. So it's around 0 to 75 kilometers thick, and it's the solid portion. It's the portion that doesn't move. Then the asthenosphere is the plastic portion. This is the portion that moves. This is the portion that's a fluid. Now, what Arthur Holmes suggested is that in the asthenosphere there are convection currents, because there's points where the heat source is greater than other points, which creates these convection cells which move, and these convection cells in the asthenosphere have experience friction with the lithosphere, which causes the lithosphere to move as well. So if I was to give you a simplified definition of this, it would be something like this. The movement of tectonic plates is related to convection currents in the Earth's mantle. And with these convection currents in the Earth's mantle, it's also two key other phenomena known as slabpull and ridgepush. And now slabpull and ridgepush we'll look into very soon. But firstly, let's have a look at convection currents. Alright, so firstly, let's take a look at convection currents. Now, I'm assuming everyone knows what convection currents are, but let me just give you a general gist of it. So the convection currents are the transfer of heat energy through the bulk movement of particles in the fluid. And when I say fluid, I am referring to gases and liquids, because convection currents can only occur in gases and liquids, because that's the only place where you can have the bulk movements of particles. Because in solids, the particles are very closely connected, and so there's no real bulk movement. The particles just vibrate on the spot, and that's not enough to make them move in circles, just like how it is in gases and liquids. So firstly, it's based on two principles, convection currents, that heated fluids expand and cold fluids, cooler fluids contract. So if I was to have, let's say, a beaker over here, and my heat source is here. Now, it's filled with water, right? Now, this top part is obviously not that close to the heat source, and so it's going to be colder. Now, since this is a colder fluid, it contracts and hence is less buoyant. It's more dense and less buoyant. Since it's cooler, more dense, less buoyant. Now, since the bottom part, so let me just draw a dotted line. Now, since the bottom part is getting heated up and it's closer to the heat source, it's going to be hotter. So since it's hotter, the particles are going to vibrate, and they're going to take up more space, which means it's going to be less dense. And since it's less dense, it's also going to be more buoyant. Now, since the bottom is less dense and more buoyant, and the top is more dense and less buoyant, what's going to happen is the top part is going to tend to move downwards, because it wants to, that's the position that it suits the best. And for the hotter part, it's going to want to go up, because it's more buoyant, and that's the position that it suits itself the best. So the cooler part is going to go down, and the hotter part is going to come up. And so once the hotter part reaches up, it's further away from the heat source, which means it's going to heat up, it's going to cool down, and this process, and once it cools down, it's going to come back down, and the heated part is going to go back up. It's going to keep on doing these cycles, and this single cycle is known as a convection cell. And to describe the entire thing, we use the term convection currents. So this is basically how it works in a simple application when you're heating up water. Now, similar to this, Arthurholmes suggested that similar occurrences happen in our asthenosphere. So he suggested that basically the heat that moves the mantle, the fluid part of the mantle, which is the entire thing, is radioactive elements. So there are lots of radioactive elements in the mantle, and that were formed during Earth's creation, and now as these decay, as let's say uranium decays, it's going to let off heat, and this heat powers movement in the asthenosphere, and so it's going to create these convection cells. So similar to what's here, it's going to happen over here. And now on top of this, we're going to put the lithosphere. So all of this bottom part is our asthenosphere. This is the plastic portion of the Earth's layers, and this part, this solid portion, is the lithosphere. This is the this is the solid portion. This is what we commonly refer to as the crust, but they're not exactly the same. So basically, as this hotter magma rises and this cooler magma forms, what's essentially going to happen is that they're going to move in these convection cells that I show here, and now the movement of the asthenosphere comes in contact with the lithosphere. So what happens here is that there's friction created, and so this friction drives the movement of the lithosphere. This is what causes, and in this case, what we can see is that this arrow is moving, this part of the convection current is moving this way, this part of the convection current is moving this way. So they're moving apart, and when they move apart, we call that a diverging plate boundary. Diverging. We don't need to know this yet. This is not the topic of our video, but I'll just put it in there. So this is known as diverging, and since this is coming, they're both coming towards each other, and one is going under the other, this is known as converging. This is a converging plate boundary. Now, one thing you notice is that one plate goes under the other. This is known as subduction. Alright? This is known as subduction, when one plate goes under the other, and it's often just heated up and it's just recycled. So now that we've got this convection current part done, let's look at the two key phenomena known as slabpull and ridgepush. So when we first looked at convection current as part of our convection current theory, we learned that friction pushes the plates, the friction between the lithosphere and the plastic asthenosphere pushes the lithosphere into the same direction in which the asthenosphere is moving. Now, that's not the only reason why plates moved as suggested by the convection current theory. There's two more reasons that were discussed in our definition, and these are ridgepush and slabpull. So what exactly is ridgepush? So ridgepush and slabpull, firstly, both of these theories talk about how the lithosphere interacts with the asthenosphere. So firstly, ridgepush. Ridgepush suggests that new oceanic ridges lie at a higher elevation than the adjacent plate, which means that basically, firstly, let's see that we looked at our convection current. So let me just quickly draw up the basic convection current that was in the previous diagram. So we already know that these two plates are going to be diverging, as we said, and these two interact in a converging manner. So for ridgepush, we're firstly looking at how these plates diverge. So this part over here. And we looked at the convection currents behind it, and basically what's going on is that there's two parts. So there's, out of the convection currents, there's 2 points where they're both rising. So since both convection currents rise at the same point, the magma pushes upwards. And hence, since the magma pushes upwards, what essentially happens is that the plate, which was originally something like this, also gets pushed upwards. And so now the plate is like a mountain. Now what's going to happen is that since this place is filled with magma and the plates are upwards, gravity is somehow going to want to bring it down. So gravity is going to push it downwards like this. But since there's already magma over here, the plate can't really go anywhere. So what ends up happening is that the plates start moving sideways in a diagonal manner. And so they, in a way, they're moving apart like this. So if this was my two plates, magma comes from here, these plates go at a higher elevation, and since they're at a higher elevation, gravity is going to want to push them down. But it can't really, because there's magma over here. So what ends up happening is that it gets pushed apart sideways. And then this extra space that's created over here gets filled with magma again. And this process continues happening. So the ridge and its formation pushes the tectonic plates apart, and which causes them to diverge. And since they diverge, there's more magma that gets revealed. But the key part is that they move apart. So that's all we need to know. So if I was to write this down, I'd say something like, and a key part to remember with ridges is that they only tend to happen. They can happen, for example, in Iceland on continental crust, and that's crust that's land. But they usually tend to happen in crust that's inside the oceans. This is known as oceanic crust. Now, remember that oceanic crust is different from continental crust. It's just they're not differentiated by the way their location. They're also differentiated in their density, the materials they're made out of. So when we're generally talking about ridge push, we're only just looking at oceanic crusts, because from what we found and what we will discuss in the seafloor spreading theory is that most convergence only really happens in the ocean. So when we talk about ridge push, what we're really looking at is the ocean. But if you would like, you can put a more generalized definition of it in your notes. But this is the definition that I give you. Oceanic. So, new oceanic crust lies at a higher elevation than the rest of its plate. Gravity pushes this elevated lithosphere down and hence towards the sides because of the magma which takes up the spot, and it's not allowing the plate to just directly push down. Now with slabpull is that as we looked over here, now let's look at slabpull. As we looked over here, this part is converging, that's this part over here. But as you notice here, there's some parts, sorry, this part is diverging. As you notice here, there's some parts that are diverging, and this means that they're coming in together, they're closing in. One plate is going under the other. And so what happens here is that what pushes one plate, what causes these plates to move, in the movement of these plates, it's driven by another process called slab pull. This is where the convection current comes down. So here the convection current is coming down. So at first, the friction, as we discussed before, the friction between the asthenosphere and the lithosphere moves this plate this way. But after a certain point, because of the crust that gets subducted underneath, just enough crust is subducted so that the plate just starts going down on itself. So since the lithosphere is much denser than the asthenosphere, and this is because the lithosphere is a solid, right? It's much denser than the asthenosphere. It sinks down. So it tends to sink down when it comes in contact with the asthenosphere, and it sinks down because it's firstly more denser, and secondly it's the friction of the convection currents. All right, and so eventually, as more of the plate gets subducted, eventually the entire plate is pulled down. So since at first there's only a small amount of the plate that's getting pushed down, and that's because of the movement of the convection currents, and the lithosphere is has a tendency to just sink because it's denser. But eventually what happens is that as more plate gets subducted, it just starts going down. It's like watching a slinky go downstairs. At first it's very hesitant, but as a certain amount of it touches the next stair, it keeps on going and it keeps on going and it keeps on going. So similar here, at first it's only driven by very weak forces, but at one point it has enough force to just go down by itself, because there's so much mass that's getting subducted that's just pushing the entire plate as well. And if we were to write something for this, we'd say something like, since the lithosphere is much denser, lithosphere So since the lithosphere is much denser than the asthenosphere, it sinks down. And as more plate gets subducted, and subduction is the process where the lithosphere goes into the asthenosphere and starts melting. Since more plate gets subducted, the entire portion of it is pulled down. That's how I would give you a formal definition of slab pull if you were to write it in a test or something. So now that we've looked at convection currents, and in that we've specifically looked at just convection currents in general, and then these two mechanisms, ridgepush and slab pull, which also come under convection currents, it's time we look at seafloor spreading. Now this one's quite a hard one to understand. I'll try and make it as simple as possible there. So let's just jump straight into seafloor spreading now. Alright, so now that we've looked at continental drift and convection currents, let's look at seafloor spreading. Now, basically what seafloor spreading is, it's just a remodeling of the convection current theory, but it's applied to a specific point where we're only talking about the sea and the sea floor. And let me just point this out, that unlike continental drift, the convection current theory and the seafloor spreading, both of these were accepted, because while continental drift had evidence that supported that the plates must have been connected, the continents must have been connected at one point and then they had since drifted apart. Continental drift didn't really have an apparent mechanism, whereas seafloor spreading and convection currents, they not only had evidence, but they also had an apparent mechanism. So they had both, and they worked in unison very nicely, and they explained it very naturally, and so they were accepted. So this and this and convection current, both of these theories were accepted, but continental drift wasn't, because due to the lack of explanation, because Alfred Wegener didn't really relate cause with effect there, and so although he had evidence, although he knew what was happening, he couldn't really explain why, and so the theory was rejected. Now let's look at seafloor spreading. So as I said, seafloor spreading is just a remodeling of the convection current theory. It's just convection currents applied to the sea. Now this theory was proposed by a man called Harryhess. So basically, he took the idea of convection current theory and he matched it up with evidence that he found during the World War, when they were mapping the ocean floor during World War II. So basically, when they were mapping the ocean during World War II, they found a few key pieces of evidence that suggested that new ocean floor was being created at the middle of the oceans. So why don't we, to start with, take a look at the convection current theory and build upon it so that it leads to the seafloor spreading theory. So we know that in the convection current theory that there's convection currents under the Earth's lithosphere. So just a reminder, the solid portion, this is the lithosphere, and then the plastic portion of the Earth's layers, this is the asthenosphere. Just remember this, and this, the lithosphere, and this is how these are separate plates, and this is how the convection currents are moving in this case. And since this is seafloor spreading theory, these are all this is a piece of oceanic crust. So where the divergence happens, where the plates are moving apart, as we learnt in convection currents ridgepush, this stuff only happens on oceanic crust, because this is specific to the sea floor. So firstly, we know that there's convection currents in the asthenosphere, so there's obviously going to be convection currents under oceanic crust. So this is your oceanic crust. There's obviously going to be convection currents, because there's convection currents everywhere, as suggested by the convection current theory. So let's quickly just write that down. Under the ocean, there are convection cells, or convection currents. Cells. So a cell is basically just a singular convection current, so just one movement, and these two combined would be convection currents. So we know that there's convection cells under the ocean, and the plural form convection currents, and in this case we can see that two convection currents, both with their rising part, are meeting, and so as explained by the phenomena of ridgepush that we discussed in the convection current theory, when we have two when we have two rising layers of, like, when you have two rising magma, what essentially happens is that the crust gets pushed at a higher elevation than the rest of the plate, and so which forces the plate, or which causes this point to split. So we can say this as where two convection splits. So where two convection cells meet and both are rising at the ocean, this is implied, the ocean floor splits. So as you can see, the ocean floor is splitting. And why does it split? Because we've already discussed this in the phenomena of ridge push. Alright, so we know that the ocean floor is splitting, all this is happening, and now let's link it back. Now let's understand why the seafloor is actually spreading, because the seafloor spreading theory kind of explains why the seafloor spreads. So for seafloor to spread, then it's going to be moving apart, and then there's going to be new seafloor being created. So then how is this new seafloor being created? Basically what happens is that you have magma that's moving around in convection currents. Now the seafloor has split over here, so the magma can come out, and so once the magma comes out, it takes up the space. And since in ridge push we know that the plates, due to gravity, start moving diagonally, there's going to be extra space created, and so then to fill up this extra space, we're going to have the magma that's in the asthenosphere, and so it's going to fill up this extra space. It's going to cool down, and then this extra plate, and this plate that's getting pushed, it's eventually going to get pushed, and it's going to get subducted into this subduction zone. And this process is going to be slab pull. So we can write something like this: at the location of the split, at the of the split, at the location of the split, Alright, so at the location of the split, this point, the magma comes out as basaltic lava. So since it's underground, since it's under the sea, it's gonna come out as basaltic lava. This adds to the oceanic crust. At this location, rifts and mid-oceanic ridges are formed. So basically what's happening is that magma comes out, it's filling in the empty space that is caused by these plates moving apart due to the convection currents. And so once this portion is filled apart with basaltic lava, there we go, new crust created. New crust created pushes the other tectonic plates apart, and so this new crust is essentially connected to the existing plate. So new crust created, connected to existing plate, the seafloor spreads apart. So there we go. That's your seafloor spreading apart, because the plates are moving apart, new crust is getting constantly created. So essentially, in a way, the seafloor is getting spread apart. Now, we talk about, in this point, we talk about mid-oceanic crusts, mid-oceanic ridges and rifts. These two landforms are formed. So what exactly are rifts and mid-oceanic ridges? So if we come back to this diagram over here, it's quite messy. So I'll just quickly erase this. Alright, so if we look at this portion of our diagram, this is just a zoom in of that portion of our diagram. So we know two things: that the point where the magma is pushing upwards, it's going to be at a higher elevation than the rest of the plate. So as you can see, the magma is pushing upwards, which makes this point, the points closest to where the magma is pushing upwards, at a higher elevation than the rest of the plate. So this point of higher elevation is the entire point of higher elevation is referred to as a ridge, right? And then if you notice one thing, okay, so when they were mapping out the ocean floors during World War II to find paths for the submarines and stuff, they found that there were these ridges, there were these high elevation points, and these high elevation points were really close to the middle of oceans. So if this was the span of your ocean, they'd find that the ridge is located really close to the middle. Now how close this often changes depending on the ocean, because all the plates move at different rates. Not every plate moves at 5 centimeters a year, let's say. One may move at 1 centimeter a year, other may move at 3 centimeters, and then one plate, due to which they're never at the middle. They can be very close, but they're often just but they're around that proximity. They're around the middle. But anyways, we'll assume that in this case, this is a perfect ocean. These two plates are moving apart at exactly the same rate, and so the mid-oceanic ridge is literally just in the middle. So what they found is that in the middle of these oceans, there were these ridges, because that's where the magma is coming out from. Now, another thing they found, that on top of these ridges, there were these small valleys, these V-shaped depressions. And so these V-shaped depressions, they mapped them out into something called the Great Rift Valley. So basically what this V-shape is, this specifically is a rift. And once they mapped out the entire connections of these V shapes, they called it the Great Rift Valley. So if you were to search up the Great Rift Valley, you would find the entire network of all these rifts and stuff. Alright? So this is basically the two key landforms when it comes to seafloor spreading. And now we've looked at the key processes. This is how we go from convection currents to seafloor spreading. This is how we use convection currents to explain how seafloor spreading works. So then, if I was to give you a definition of seafloor spreading, it would be something like the gradual widening of an ocean basin as new oceanic crust forms at a mid-oceanic ridge axis and then moves away from this axis. So let's quickly write that down as well. So the gradual widening of an ocean basin as new oceanic crust forms at a mid-ocean ridge axis and then moves away from the axis due to convection currents in the asthenosphere. This is how you would define seafloor spreading. Now, this is the process, this is the theory, and it makes sense how seafloor spreading works. But then now we get to the hard part. Now we get to the part where Harry Hess came up with this evidence. Now we get to the part where Harry Hess explained his train of thought. He explained what evidence he had to support that that there's actually movement in the ocean, and there's new crust that is constantly being created at the point of the ridge. So now let's quickly take a look at the evidence that Harry Hess had to support his seafloor spreading theory. And then after that, we'll jump into plate tectonics. Alright, so before we get started with the evidence for seafloor spreading, I thought I might give you the definitions, or I thought I might hit you up with the definitions for rift and ridges. And these are the formal definitions. So if you get asked in a test, this is what you would want to write, something along the lines of this. A rift is a depression in the Earth's crust caused by the spreading apart of plates or rocks. A ridge is a 2-kilometer high submarine ocean belt that forms along a divergent plate boundary. Now, divergent isn't something that we've looked at. Divergent plate boundaries, convergent plate boundaries, that stuff comes in the plate tectonics theory. So we don't really need to worry about that. But divergent just literally means spreading apart. So if these are two plates, divergent means they form along the spreading apart of two plates, so around in this area. Okay, so now let's just take a look at the evidence they had for seafloor spreading. So first of all, the first and most really obvious evidence that they had was the presence of rifts and mid-oceanic ridges. This is just a shortening, but the presence of rifts and mid-oceanic ridges. So if you think about it, if you look at the concepts of slab pull and ridge push, especially ridge push, it makes a lot of sense from the convection current theory for the existence of mid-oceanic ridges to be associated with tectonic plates moving apart. So really, honestly, the existence of these landforms, and especially the mid-oceanic ridges, kind of prove the notion that ridge push is something that is occurring at the middle of the ocean and spreading apart the sea. So really, the presence of rifts and MOR, it sits very nicely with the convection current theory. It fits very nicely, which explains why this seafloor spreading theory can be. That's just how mid-oceanic ridges are evidence for seafloor spreading. Now the next piece of evidence that they found was the presence of trenches subduction. Okay, so we've discussed ridge push and how the presence of mid-oceanic ridges kind of proves the notion that there's new seafloor being created at the middle of the ocean. But another way of looking at it is also the presence of trenches. The presence of trenches at subduction zones. Alright, so as we know, if a plate's getting pulled apart here, and let's say this in most cases this is how it works. The two plates that are getting pulled apart, they're the two plates that are the entire span of the ocean. That's the width of the ocean. And then when this width of the ocean, this is all oceanic crust. So this part is with all oceanic crust. Now, when the oceanic crust comes in contact with the continental crust, so this part is the continental crust. What tends to happen is, because the continental crust is much less denser and lighter than, it's much less denser and much more lighter than the oceanic crust. What tends to happen is that the oceanic crust goes below the continental crust. It sinks in, and what happens is, because it's getting separated here, it's gonna have to go somewhere, and it eventually sinks in at this point. So it sinks in, and what happens here is that it gets recycled in through a process known as subduction. So when it gets recycled, you may see is that there's this tectonic plate, and then you have this one getting recycled. So it creates this depression. So this depression, or what we kind of refer to as a geosynclined depression, this is just a smart way of saying trench. It helps you sound like you're using the correct terminology, which basically is equal to a trench. So this geosynclined depression is created when one plate subducts under the other, and this zone is known as the subduction zone. Now, the existence of a subduction zone, and hence the trench, is only possible if the plate is going under the other, and the plate can only go under, the oceanic crust can only go under the continental crust if we know for a fact that it's getting pushed away from the mid-oceanic ridge, and hence new seafloor is being created. So since it's getting pushed away, since it's getting subducted, we know that at another point, since this part is getting pushed inside, at another point seafloor oceanic crust is being created. So it gets created over here and it gets pushed down. So hence the existence of trenches at subduction zones also prove the seafloor spreading theory. Now, a subduction zone, let me also give you a formal definition for this. A subduction zone is where cold, and subduction zones relate to slab pull. Subduction zones relate to slab pull, and in the convection current theory. So when we talk about slab pull, we're talking about subduction zones essentially, where cold oceanic crust sinks into where cold oceanic crust sinks into the mantle and is recycled. Alright, so these are two pretty basic pieces of evidence, right? Now we get to the more technical and more really interpretive, like really interesting pieces of evidence. This is the part where we look at dating techniques and all that. So this is the part where it's a bit more complicated. Next two pieces of evidence. And it relates to when they were mapping out the ocean floor for submarines during the World War. Okay. So, third piece of evidence, they found that if you look at if you take the point of the mid-oceanic ridge as your starting point, and then you move symmetrically on either side, and then you collect samples of rocks. So in this case, rock A, rock B, and rock C. So they moved equidistant from the mid-oceanic ridges on both sides, and then they collected samples of rocks or sediments. And what they found was that the age, and so then they did some dating, like radiometric dating and stuff, and then they found that the age of the ocean floor increases symmetrically from the ridge. So if you were to look at the rock at the left side of the ridge, so this A, let's look at rock A, and you were to date it and find that, okay, well, this is 5 years old, but that's not how it works. This is just an example. And then you will look at the rock B and see, oh look, this is 10 years old. And then rock C, this sample is 15 years old. And so let's say this is the distance you moved from the mid-oceanic ridge to A, and you move that same distance on the other side, and you find that the rock that you collect there is also 5 years old, and then the rock from B is also 10 years old, and then the rock from the mid-oceanic ridge to C is 15 years old. So what they notice is that the age increases symmetrically. It's not that this part is the least age and this part has the oldest rock. It increases symmetrically from the mid-oceanic ridge. And this is only possible if new crust is being created at the oceanic ridge, and then it spreads apart over time. And another thing that they used to back this up was that if you looked at, let's take a look at this part of the ridge, this part of the plate. They noticed that, and so let's bring that over here. They noticed that when they measured the amount of sedimentary rock, they noticed that if you go further away from the ridge, you're likely to find more sediments than if you're closer to the ridge. So the amount of sediments that are gathered on the plate increase as you go further away from the plate, hence also suggesting that there's new oceanic crust being formed at the ridge. And so that's that. And then finally there was the theory, there was the evidence of paleomagnetism. This is a quite interesting one. In fact, I might as well just take up all this space. Alright, paleomagnetism. So, what essentially paleomagnetism refers to is the record of ancient magnetism preserved in rock. So paleomagnetism refers to the record of ancient magnetism preserved in rock, but what we're exactly looking at in paleomagnetism is this thing called magnetic striping. Alright, so we know that many rocks, and we learned that basaltic lava comes out to form new oceanic crust. So many rocks formed underwater from volcanic activity. So that's something that we can assume, right? Because it's basaltic lava, and so it's you can think of them. You can think of the ridges as you can think of the process of ridgepush as just small volcanoes. So the rock is really just volcanic, and so basalt, which we talked about basaltic magma being created. So that's what's being created. Basaltic lava rises, right, and sets as basalt, just basaltic rock. And so they found that basaltic lava melts to create basalt, and they found that basalt contains something called magnetite. magnetites. Now, what is this magnetite? Magnetite is just a metal, or like a form of a metal, and so it has a north-seeking pole and a south-seeking pole, similar to a magnet. So, then they had magnetite, which has a north and south pole. So if I was to let off magnetite in the in lava, it would arrange the north in a fluid. It would arrange its north and south poles to align with the north and south poles of the Earth today. And so what they found is that we'll need another diagram for this. I'll just what they did was that they took a bird's eye view. Let's say this is the span. This is the top view of this top. This is the ridge. And what they saw was that as they went away, and so we know that basaltic lava, firstly, we know that basaltic lava contains magnetite, and so magnetite has a north and south seeking pole, and when the when the basaltic lava solidifies, the north and south poles that were in the magnetite get stuck in there. So and we know that our north and south poles change. So let's say this is one stripe of, so let's say this is the ridge. This is where all our basaltic lava comes out from, and it solidifies to become rock, right? So let's say the latest one. So this is what's going on now. We know that the north pole is here and the south pole is here. So what would happen is that as the basaltic lava would solidify, the magnetite would arrange its poles, so that the magnetite's north pole would arrange itself with the Earth's north pole. Similarly, the magnetite's south pole would arrange itself with the Earth's south pole. So this is what it would look like, right? But as they went further away, so then they go one more away, and what these geologists find is that the poles switch. They do the same for the other side of the ridge, and surprisingly, the poles switch. Then they go a bit further, the poles switch back, and this is what is collected. This is what is collected by the magnetite as it solidifies, because it solidified way back and it collected the information of the poles at that time. So when they notice changes in where the North Pole and the South Pole are located, they realize that first of all, the patterns on either side of the ridge are symmetrical, and so they have those magnetic fields pointing in the same direction. So these two, both on the ridge, go up. These two, both on the ridge, go down towards north. And so this suggested that this can only be possible, this symmetry, because you can't have that symmetry, let's say over here, or you can't have that symmetry over here. This symmetry can only be possible at the mid-oceanic ridge. And so from this they learned two things. The first thing is that our magnetic fields switch. This is how they discovered that our magnetic fields constantly switch. And as we all know, we're quite overdue for the next one. And secondly, they realized that the magnetite and hence the basaltic lava must be coming from the ridge. So the magnetite and hence the basaltic lava, or you can say the same thing with basaltic rock, must be originating from the ridge. And so that's what they found. And since another thing, and this might be a bit complicated, they noticed that the ridges, these poles, these lining of the magnetite, they were parallel. All this is parallel with the ridge. And so if your north pole was at this point and it was parallel with this part of the ridge, if one of your poles was at this point and it was parallel with the ridge, it could only be so that this part was parallel at one point when the rock solidified. This portion, these two portions of the rock were over here, and so hence they were parallel. Otherwise, what would have happened is that they would have come at a slant. If the rocks were to melt at this point, they would have slanted towards the pole instead of staying parallel, which also suggested that there was new rock being created at the ridge, and it had been solidified there as well. So that's your evidence for seafloor spreading, and that's seafloor spreading done. And I know this is quite difficult to understand. I'm going to have notes, and like succinct notes with not this kind of explanation, but more of what you would want, like formal definitions and stuff, attached in the description of this video, and I'm pretty sure the pinned comment. So just quickly check that out, and you find succinct notes on the four geological theories. So now that we are done with seafloor spreading, let's move on to our final theory, plate tectonics. Plate tectonics is basically just a combination of convection current theory and seafloor spreading theory, and this is where a bunch of our terminology comes in. Plate tectonics is where we look at things like plate boundaries, plate movements, and all that. So yeah, let's just do that now. Alright, so now that we've looked at the previous three theories, it's time to look at the final theory, which is plate tectonics. Now, plate tectonics is a theory that is the most overarching one out of all of them. It's the one that overshadows convection currents and seafloor spreading. It's the most important one, and in a way, it's formed. The entire plate tectonics theory is formed from taking information from from taking information from convection currents and seafloor spreading and combining them to come up with this theory. This is the final theory, and this is the pretty much the overarching theory. This is the theory that can be used to explain seafloor spreading and convection currents, and this can be done vice versa as well. So, plate tectonics was a theory proposed by a person called wjmorgan. Now, before looking at now, plate tectonics is a theory that is heavily based around how plates move. So when we did seafloor spreading and convection currents, we learned two key methods in which plates move. So we learned that they go apart from each other. This is called diverging, and another one that we learned was that they go into each other, as in they go like one goes over the other or something like that happens. This is called converging. And there's another one, so there's three. But before we look at those types of plate movements which form a major part of the plate tectonic theory, I think it's important to look at the key definitions, get everything right, because we've been talking about many key terms and it's time to define them. So before we look at the different types of plate boundaries, I believe it's really important to come up with formal definitions of everything that we've looked at so far, and everything hence that is part of plate tectonics theory. So to begin with, let's define plate tectonic, the theory itself. So plate tectonic is the theory that the outer layer of the Earth, the lithosphere, consists of separate large plates. lithosphere consists of separate large plates. Now, these plates are usually larger than the continents. And they also move with respect to one another constantly. So this is the formal definition of plate tectonics, the plate tectonic theory. Now there's two key aspects when it comes to the definition and the theory itself. Two key sub-points that we need to know: that as a plate moves, its internal area remains mostly, but not perfectly, rigid and intact. As the plate moves, its internal area remains mostly but not perfectly rigid and intact. That's the first key point. And another key point that we need to know is that rock along plate boundaries undergoes intense deformation as the plate moves. Rock along plate boundaries undergoes intense deformation as the plate moves. So this is basically the key definition for plate tectonic theory, and then we've also got the two main points that we need to remember when it comes to this theory, because these two are usually what create the explanation questions in tests, so it's good to know them. Now let's look at another definition, and we'll also look at the different layers of the earth, because that also becomes part of plate tectonics. So this is the key definition. This is the definition if someone asks you what exactly is plate tectonics. This is how you would succinctly explain it. Now we'll go into the more deeper aspects of the theory itself. So now that we've looked at the overarching definition, let's just straight up get into the smaller and more refined aspects and the deeper aspects of the plate tectonic theory. So the first part of understanding plate tectonics is understanding plate boundaries. So the second definition we want to know is plate boundaries. So we usually talk about when we did seafloor spreading, we were talking about how there's two types of plate boundaries: converging and diverging. Diverging moving apart, converging going crashing into each other. And so plate boundaries is just a way to describe the types of we're using the term plate boundaries over there to describe the type of connections and the movement, the relative movement of each plate. So the definition of plate boundary would be the border between two adjacent lithospheric plates. The border between two adjacent lithospheric plates. This is plate boundary. Now, just so we can get ourselves ready for what's going to come next. There's 3 types of plate boundaries, so you would want to note these down as well. We're obviously going to look at them much more closer in a bit, but the 3 types are converging plate boundaries, diverging plate boundaries, and transform plate boundaries. So these are your 3 types. So remember them. Now let's look at the layers of the earth. Let's look at the basics of it, because to understand how the layers of the earth are actually organized, it's going to be very complicated. So let's look at only the key terms that we're going to be using in the study for plate tectonics. So let me draw it over here. So you will have your crust. Actually, alright, so this first part is my crust. This is the part that they say is as thick as as thick as apple skin when you consider the apple as the earth. So this is the crust. Then you have the mantle. So this is all the hot bits. Your mantle. This is all the hot bits. Then you have your core. Now, your crust, the size of your crust can depend, because there's some parts that there is no crust. They're just exposed to magma, and there's some parts where the crust is very thick. But so then we can say that the range for the crust is 0 to 75 kilometers. Now for the mantle, there is no range. We have an approximation. The approximation is 2,900 kilometers. This is how thick the mantle is. And then for the core, we have, this is also an approximation, 3,470, my bad. 3,470 kilometers. So this is how thick the core will be. Now, another way to look at it is in terms of lithosphere and asthenosphere and all that. So, lithosphere. So, first of all, let's just quickly take a look at our mantle. For this, we identified this as our mantle. So, when it comes to lithosphere, this part is our lithosphere. So, what's the difference? Well, the lithosphere can be defined as the crust plus the uppermost solid mantle. So, lithosphere is our uppermost that's your lithosphere, the crust and the uppermost solid mantle. Then you have the asthenosphere. And these are the only 2 key ones that we need to know for now. So then we have the asthenosphere. And the asthenosphere is the plastic portion of the mantle. The plastic portion of the mantle. And we can say that the lithosphere flows over the asthenosphere. So the lithosphere flows over the asthenosphere. So this is this is the dissection of our Earth, and this is the approximate values. This is approximate thicknesses of each of these parts. And then for the core, you have the outer core. So the core can be divided into two: the outer core and the inner core. So the outer core is 2,200 kilometers thick. And your inner core is 1,278 kilometers thick. And your outer core is your outer core is I'm pretty sure the outer core is liquid, and no, sorry, the outer core is solid and the inner core is liquid, or it might be the other way around, but I'm not really sure. You can search that up. But yeah, so the core can be divided into the outer core and inner core. Yeah. So now that we know about the definition of plate boundary and we know about the layers, let's now take a look at the types of crust. So we have two types of crusts, and we've discussed this in seafloor spreading as well, and it's really important. The two types of crusts. So the first type of crust, so this is our fourth point, because our first point was the formal definition of plate tectonics. Then we looked at plate boundaries, definition of them. Then we looked at the layers of the Earth. Now we're looking at the types of crust. So your first type of crust is oceanic crust. Now, oceanic crust is the crust that forms the ocean floor. Quite simple. And then continental crust is the crust that forms the continents. So oceanic crust is the crust that forms the ocean floor, and the continental crust is the crust that forms the continents. Now, what's really the difference between oceanic crust and continental crust? Because apart from the fact that one is underwater and one is above the water. So oceanic crust is darker, thinner, and denser, as it has less silicon and heavier elements such as iron and magnesium. So if you're asked about a key differentiating factor between oceanic and continental crust, you can say that oceanic crust is much darker, thinner, and denser than continental crust. So oceanic is darker, thinner, and denser than continental crust. And why does it have these traits? Because it has, firstly, less silicon and heavier elements. It has heavier elements such as iron and magnesium. There we go. So this is what separates oceanic crust from continental crust. And if I was to show this on a diagram, oceanic crust would be something like this. This is oceanic crust, whereas continental crust would be much larger, but not as dense. And so what tends to happen is that whenever we have the ocean meeting the continents, there's this we know that the denser plate will tend to sink under the less denser plate. From what we learned in seafloor spreading and convection currents, is that if I have a plate that's more denser, more heavier, it's going to want to go down rather than more than the plate that is lighter. So what's going to happen is usually, and to be honest, in all cases, the oceanic crust, because it's denser, because it's heavier, it's going to move under. It's going to move under the continental crust. So yeah, that's the difference. And another point to note is that because the reason why continental crusts are so voluminous, they're so less dense compared to oceanic crusts, is because it also explains the fact that that's why they are at a higher elevation, because continental crusts are only so big, and this is equaled out by the amount of water that is on oceanic crusts. So it makes sense for continental crusts for them to be at a higher, to be less dense, more stretched out than oceanic crusts, because it's the reason that they lie on top of the water, while oceanic crusts are much more dense and they don't take up as much space, which causes water to go over them. So that's the difference between oceanic crusts and continental crusts. So now let's look at the three different types of plate boundaries. So firstly, we'll look at, so we know, as we know from earlier, three types of plate boundaries are diverging, converging, and transform plate boundaries. So firstly, let's take a look at diverging. So, point 5 of plate tectonics, plate boundaries. Alright, diverging boundary. Right, a diverging boundary is where the plates are moving apart from each other. And this is noticed at mid-oceanic ridges, alright? So, diverging plate boundaries, in fact, you will probably most likely only notice them at mid-oceanic ridges, because the seafloor spreading was so well made, and when they took the plate tectonic theory and when they put those two theories together, they kind of realized that there's, if you search up plate boundaries, they kind of realized that there's no there's no really any other place where you'd find a diverging plate boundary apart from mid-oceanic ridges. And you can search up types of plate boundaries over and map types of plate boundaries map, and it's going to come up, and most of the diverging boundaries, they're going to be located where the mid-oceanic ridges are, and that's what we know from seafloor spreading. So we'll look at this in terms of seafloor spreading. This doesn't necessarily mean that they have to be, when we talk about diverging boundaries, but this doesn't necessarily have to mean we're talking about mid-oceanic ridges and seafloor spreading. This can also, in some very rare cases, refer to just a continental crust and two pieces of continental crust, or two pieces of continental crusts with magma coming from underneath. But anyway, let's look at diverging boundaries in terms of the ocean, because that's where they're most prominent. So this is where this is coming back to convection, current, seafloor spreading. But we'll just leave this because we've already looked at this. We'll just leave this with a basic definition, a basic annotation. So the magma rises into the rifts and solidifies to form new crust. Solidifies to form new crust. This pushes the two tectonic plates apart. This pushes the two tectonic plates apart. This is something that we can write for explaining diverging boundaries in terms of mid-oceanic ridges. Now, this doesn't necessarily diverging boundaries, as I said, don't necessarily have to happen at mid-oceanic ridges. They can also happen on continental crust. And an example of this is Iceland. So, if we look at Iceland, Iceland has a diverging plate boundary right damn smack in the middle, and so this is causing Iceland to actually be actually split into two and keep on moving apart. Because Iceland is right on top of a mid-oceanic ridge, and it's continental crust on top of a place where there's mid-oceanic ridges, so it's happening on continental crust. This is how diverging boundaries occur on continental crusts. And yeah, and so in this case, Iceland, this is the mid-oceanic ridge going over Iceland, and it's breaking apart, it's spreading apart. So this is just your diverging boundary happening in Iceland, and this process is known as rifting. So what is rifting? Rifting is the process by which continents break. So the crust cracks and subsides, which allows water to flow in, and then seafloor spreading occurs. So in this case, in the case of Iceland, this rifting is occurring. And if you also look at the African and Arabian plate, they are spreading apart to create the Red Sea. So basically what's happening, so this is Iceland. Iceland is just an example of what happens if there's a mid-oceanic ridge on top of continental crust. But if you look at the African and Arabian plate, they're actually moving apart, and because so this is our African plate, this is our Arabian plate, they're moving apart, and because they're moving apart, what tends to happen is that, oh look, there's extra space, and so because there's extra space, water tends to fill it in, so this place gets filled up with water, and this allows water to flow in, and then seafloor spreading occurs. So as you can see, it always comes back down to seafloor spreading. So if there's two pieces of continental crust and they separate, it allows water to flow in, and then seafloor spreading occurs how it would naturally occur in places like Iceland and just in the sea. So this is diverging plate boundaries. Remember this term rifting. You might want to do some extra research on it so that you can use it in test contexts, and just to sound smart. And this is also a very broad topic as well in terms of geology. Now let's look at the next type of boundary. So after diverging boundary, we've got converging boundary. So let me just, sorry. And another key thing to remember about diverging boundaries, which we were just doing, is that the motion. So this is another key part of diverging boundaries. The motion is spreading because they're spreading apart. So if you were to describe the motion of diverging boundaries, you'd say it's spreading apart, and then the effect is constructive. So what happens as a byproduct? It's constructive. And why is it constructive? New crust is created. New crust is created. Then topography. What landforms are you likely to find from diverging boundaries? You're likely to find ridges and rifts, as this is discussed as in our seafloor spreading theory. So ridges and rifts are something that you're likely to find. And volcanic activity. Yes, there is volcanic activity. Because if you remember, this might sound a bit surprising. Oh, how is there volcanic activities? It's just spreading apart. How are there eruptions going around? But you need to remember that volcanic activity does not always refer to just eruptions. It can also refer to slow magma just coming out. And so this is what happens at the seafloor. So yes, there is volcanic activity, because when the two plates spread, the magma rises, and that is volcanic activity. It comes out as basaltic lava. So they're very long volcanoes, similar to fissure volcanoes, but not exactly. So if you want to understand the volcanic activity at diverging plate boundaries, especially under the ocean, I suggest looking at fissure volcanoes. They're an accurate representation, but they're not the entire story. So do some research on that. But fissure volcanoes, I'd say, is a good place to start understanding how volcanism works at diverging boundaries. So now let's look at converging boundaries. And you don't have to necessarily refer to them as diverging and converging. You can also call it divergent and convergent boundaries. So that's another way. Now, converging plate boundaries, they're not very basic like diverging plate boundaries, that it's going to spread apart and new oceanic crust is created, new crust is created. Converging plate boundaries is a little bit different. But to first of all, just to define it, it's where plates are colliding with each other. So yeah, where plates collide. So when two plates move into each other, basically, one plate doesn't necessarily have to subduct under the other, or something like that. But it's just two plates are colliding. Where two plates collide. Where the plates that's the simple definition of converging boundaries. Now, as we learned before, there's two types of crust: oceanic crust and continental crust. Now, essentially, what happens is that this collision between the plates varies depending on what type of crust we're talking about, because we know that the two types of crust have different properties, and so they interact, and these different properties play a role in how they interact. So when they come and hit each other, they're going to do that differently. So two pieces of oceanic crust will do it differently than two pieces of continental crust. So let's look at how each combination would converge. So firstly, let's look at if oceanic crust was to move into, or oceanic and continental crust was to move into each other. So this is firstly oceanic with continental. So what would happen in this case? So the denser ocean plate would sink under the lighter continental plate. This process is subduction, as we learnt in convection currents and seafloor spreading. The denser ocean plate would sink under the lighter continental plate. This is known as subduction. Okay. Next, now let's look at the landforms that would form with oceanic with continental. So the continental plate would be distorted and it would form fold mountains and stratovolcanoes, and the oceanic plate would subduct to create deep ocean trenches. So let's take a look at this. So the denser oceanic plate is going to subduct. So this is our oceanic, this is our continental piece of crust. Basically, oceanic crust is going to subduct, so it would form deep ocean trenches. So you would find deep ocean trenches over here. And also, because this plate isn't only just getting subducted, what's also happening is that as this plate gets subducted, it's pushing this plate inwards as well. And when this plate gets pushed, it's gonna squeeze, right? And when something squeezes, it rises. It also, so basically when this gets squeezed, it's gonna become all deformed and it's gonna have a bunch of bumps over it. So this would form this would cause the rock to layer on top of each other, which would eventually cause it to rise. So this is how fold mountains would be formed. So you'd have fold mountains because the rock is getting pushed into each other, so the rock would essentially just fold. So that's how you get fold mountains. And then you'd also get stratovolcanoes. So you'd also get those volcanoes that we see, like the more common type of volcanoes. So now, how do you get volcanoes? Alright, this process is quite difficult, right? But when the oceanic plate gets subducted, it contains something called volatiles. These are easily vaporizable materials. So this includes stuff like water and carbon and all that. This stuff can easily be vaporized, especially water. So basically what happens is that there's hot magma over here, the plate gets subducted, and since there's this high temperature difference, this plate starts melting instantly. And because of the volatiles, the instantly vaporizable materials, they get evaporated really quickly, and so this plate is just really hot. And so since it's really hot, it's less denser. And since it's less denser than the rest of the asthenosphere, it's gonna rise. As we learned in convection currents, the less dense, hence more buoyant, wants to rise. So this really less dense and really hot magma is going to want to rise, and once it rises, once it reaches the crust, it's gonna erupt. And so all this lava, all this magma, now in the form of lava is gonna come out. It's gonna all erupt, and it's coming straight out. And so that eventually would form a stratovolcano. So you'd have deep ocean trenches, as you can see over here. You'd have fold mountains because the rocks are layering on top of each other, and then you'd also have stratovolcanoes. So these are the big boys. These are the volcanoes that we see. These are the volcanoes we see everywhere. These are the ones that we see in cartoons. So that's what would happen if oceanic crust was to collide with continental crust. So now let's look at a different scenario. Now let's see what would happen if continental crust was to collide with continental crust. Continental on itself. So continental crust we know is really less, it's less dense. So both are equally less dense. And so one plate, and we know one thing with converging boundaries is that one plate does go under the other. That's going to have to happen. But this doesn't necessarily mean that one plate has to subduct under the other. So in this case, since both plates aren't necessarily very dense, they're both very less dense, both are equally less dense, so both are equally less dense. So one plate goes below the other, but neither subducts, hence both are pushed upwards. But neither both are equally less dense, but neither subducts, and hence both are pushed upwards. So one plate goes under the other, and what this does is that this applies pressure on this plate. This plate gets squeezed. It starts, instead of being all straight as it used to be. So let's say this is the rock. This is the rock before it got squeezed. Now this plate is pushing. So now what happens to the rock is that because it's getting compressed, it's gonna take up a smaller space. So now the rock has to take up a smaller space. So it gets something like this. And since it's all squiggly, this is not how it works. I'm just giving you a model to understand it. Since it's all squiggly, it also rises in height. So when we push down on something, when we push down on the ball, a rubber ball, what we see is that while the height does get down, it expands in width. Similarly, while we're pushing this, it's going to expand in height. And since this part expands in height, and a similar thing happens here, because this wants to resist this motion, so it's going to push back. Every action has an equal and opposite reaction. So this is going to push back. This piece of crust is going to push back, which causes the rock here to fold as well, and that's what fold mountains are. And so then we get a bunch of mountains. We can, and in most cases this results in a mountain range. And an example of this is the Himalayas. The Himalayas, two pieces of continental crusts colliding, get a rocks layer up, create fold mountains, and you just have a big mountain range that stretches over a long belt. So that's what would happen if you had a continental crust with continental crust. Now finally, now that we've looked at these two, what would happen if oceanic crust was to collide into oceanic crust? Oceanic with oceanic. Oceanic times 2. Alright, so in this case, both are equally dense. So we can't really make both of them subduct. That's not really possible. So a key thing to remember when two oceanic crusts are colliding is that the faster moving plate tends to subduct under the slower moving plate. The faster plate subducts under the slower plate. The key thing to remember. And then this creates a chain of volcanoes as it subducts, and then these erupt and create islands. So really thin oceanic crust with another piece of oceanic crust, the oceans on top. And as we learned from how stratovolcanoes are created when oceanic crust meets continental crust, this is going to get subducted, and so the volatiles in this are going to melt. The magma is going to get hotter, it's going to rise, and then we're going to get this process, this subduction will happen. And once this plate has subducted, we're going to get a bunch of smaller volcanoes. And so these volcanoes, well, this, and since if you were to look at this from the top view, right, or what you would see is that since an entire plate is getting subducted, you're getting a bunch of volcanoes, right? And so these volcanoes are known as island arcs. So now you just have a bunch of volcanoes, and so you've just created so many islands. So this is how so once these volcanoes erupt, they create islands, and so this entire thing is known as an island arc. Now that's converging boundaries. Now let's look at the features, like the overarching properties of converging boundaries, like we did for diverging boundaries. So converging boundaries are the motion that we commonly associate with them is subduction. But remember, this doesn't always have to happen. They don't always have to subduct. But in most cases they do. Subduction, the effect is destructive. Like, this is from an overall perspective. So while, as we discussed just then, two oceanic crusts can create islands, what they're ultimately doing is they're just destroying crust. So what's the effect? They're destructive. Now, topography. A key topography is trenches. This is something that's common. Volcanoes are common, but not every time. The type of volcano differs depending on the boundary, but there's always going to be a depression, so hence a trench. There's always going to be a trench. And is there volcanic activity? Yes, as we discussed, there's going to be stratovolcanoes and island arc volcanoes, which are pretty much the same thing. So volcanic activity, yes. And the volcanic activity is usually where two pieces of oceanic crust collide, or there's one oceanic and one continental. So this is where you get volcanic activity. Okay, so now we've done diverging boundaries, we've done converging boundaries. Final part of plate tectonics, transform boundaries. So let's do that. Transform boundaries. Transform boundaries, unlike divergent and convergent, it's different because this is where two plates are sliding parallel to each other. So if I have two plates, these are my two plates, they're going to be sliding like this. And they're going to be doing this in opposite directions. So if one's moving up, the other's going to go down. So a transform boundary is where two plates slide parallel to each other. Slide parallel to each other in opposite directions. In opposite directions. The plates usually move very slowly, but there is a sudden slip based on and creates a fault. So there's a sudden slip. So these two plates are moving. They're moving really slowly, and in some cases they're not even moving because there's friction between the two. But at one point, the frictional forces are overtaken by the movement forces, and so then suddenly it just slips. So friction. You can do this with your hands as well. Hold them really close to each other and like push them together and then move them up, and then at one point it's just going to slip. So they move very slowly in opposite directions. The plates usually move very slowly. The plates usually move very slowly. The plates usually move very slowly, but there's a sudden slip. Which causes an earthquake. So, the plates, while they are moving, they're moving very slowly, and at one point there's this, and they can't really just glide past each other. That's not very practical, because the plates aren't just two rectangles that are moving. In fact, they have lots of deformities and stuff, which these jagged lines which create friction, and this friction causes them from moving, this friction stops them from moving smoothly. This stops them from just gliding apart each other, and so usually they're moving like really slowly apart, and at one point the movement force overtakes the friction force, and so this causes them to just slip apart, and this causes an earthquake. So yeah. Now, a few key points. You don't necessarily have to remember this, but it is really smart. So these transform boundaries are always perpendicular to mid-oceanic ridges. Perpendicular to mid-oceanic ridges. And an example of a transform boundary is the San Andreas Fault, which is the Pacific Plate and North American Plate. So if you want examples, you look at the San Andreas Fault. Alright, now similar to what we did with the last two plate boundaries, let's look at the main features of a transform boundary. Alright, so the motion, if you wanted to describe the motion, it would be lateral sliding. Lateral just means surface. This just means, yeah, on the surface. So the motion would be lateral sliding. Now the effect, see, with transform boundaries, there's no crust being created or destroyed. So the effect is conservative. Why is it conservative? Because lithosphere is neither created nor majorly destroyed. It's not created and it's not majorly destroyed. Topography, really nothing, no major. No major effects. There's no major effects to topography. And volcanic activity, no, there is no volcanic activity, because magma or lava or nothing like that is involved when it comes to transform boundaries. So volcanic activity, no. But there are earthquakes. But there are earthquakes. And this is why they're considered dangerous. So now we're finished with plate boundaries. Now we're finished with transform boundaries, and hence we're finished with plate boundaries, and hence we're finished with the plate tectonic theory, and hence we're finished with the 4 geological theories that we were going to visit. So if you like this video, yeah, just thank you. And if you want succinct notes on the 4 geological theories, I'll have notes. I'll have handwritten scanned notes somewhere in the description or in the pinned comment. That's it. And yeah, I mean, I was thinking about making more videos on this topic, so maybe looking at geological technology next, or landforms, or maybe even the biogeochemical cycles such as the nitrogen cycle, carbon cycle, oxygen cycle, all those cycles as well. So I mean, I can turn this into a series. That's what I was thinking, and I can also just get more knowledge to you guys and stuff. So hope you enjoyed the videos, and till then, keep studying. Alright, see you guys. Bye bye.